Hello everyone, welcome to CS 110, Chapter 9, Part 2 for BCCS and Laurel Ridge College. I'm your instructor Amit Prambat, and today we are going to discuss the remaining part for Chapter 9. Let me go ahead and share my screen. Okay, so functionality of high-level languages. Now, the chapter explores how high-level languages implement functionality, focusing on procedural and object-oriented structures. We examine syntax across multiple languages to see how features like loops, classes, and data types are expressed. Functionality of imperative languages. Imperative languages rely on sequencing, selection, and iteration. Sequencing executes statements in order. Selection chooses among actions. Iteration repeats actions in loops. These concepts mirror basic pseudocode structures. Do these concepts sound familiar? Let's review them. Boolean expressions. This slide defines Boolean expressions, which evaluate to true or false. They may consist of Boolean variables, comparisons using relational operators, or compound expressions using Boolean operators. Remember the relation operators? Let's list them. Here you can recall relational operators such as equals, not equals, less than, greater than, and so on. These operators enable decisions and comparisons in programming. Strong typing. A data type defines a set of values and permitted operations. Strong typing enforces that only value of the correct type may be stored in variables. This prevents many logical errors and increases program reliability. Data types. Here, the basic data types are listed: integers, real numbers, Boolean values, and strings. It prompts you to think of examples for each, and these fundamental types appear in almost all programming languages. Let's explore them. Integers. What determines the range of integers? Whether range vary across languages and which operations apply. Hardware, language design, and compiler decision all influence integer behavior. Reals. Real numbers are compared with integers here. While both represent numeric data, real numbers use fractional values and are stored differently. Their precision and behavior vary among languages. Characters. Here we review ASCII, extend ASCII, and Unicode. The slide asks you how many characters each supports and discusses relational comparison between characters based on numeric encoding values. Booleans and strings. Here we revisit Booleans, true or false, and strings, sequences of characters. The slide asks about Boolean uses and string operations like concatenation, comparison, and length determination. Declarations. Declarations associate identifiers with variables or actions. A reserved word has special meaning in the language. The slide notes that some languages treat uppercase and lowercase letters as equivalent. Here is a declaration example. So the table shows languages and variable declaration for those languages. We see that Python requires none. In VB.NET, they do a declaration like dim sum, and C++ Java does have something like float, int, etc. to declare a variable. A named constant, by contrast, in the declaration, this is how you can easily visualize how it would work. Syntaxes differ across languages and concept remains constant. Now let's move on to assignment statement. Assignment statement is an action statement, not a declaration, that says that to evaluate the expression on the right-hand side of the symbol and store that value into the place named on the left-hand side. And named constant, by contrast, stores a fixed value and cannot be changed. This distinction is essential for writing reliable programs. Input or output structure. High-level languages treat input as characters streams divided into lines. Data types determine how characters are converted to bit patterns and vice versa. This slide connects pseudocode operations like read and write to real programming language behavior. The data type determines how characters are to be converted to a bit pattern input and how a bit pattern is to be converted to characters output. So for input-output structures, here we see an example of input format, a string, an integer, and a real. The order matters because languages convert each input based on the expected type. Understanding input parsing prevents runtime errors. Here the table shows us languages and how their input and output statements are. So C++ has double greater than, double less than for C in and C outs. Java, you basically have those variables where you take the input in. Python does it in similar way, and VB.NET uses windowing. These languages must parse and interpret text according to type expectations, driving how data flows into a program. Control structures. Control structures determine execution order. The slide asks you to recall pseudocode control structure, sequencing, selection, and iteration, and recognize how they manifest in actual code. Selection statements. Again, we see a table that has a language and if statements. If statement allows program to test the state of the program variables using a Boolean expression. An if statement tests Boolean expressions to choose actions. Here we see an illustration of core structure of conditional branching, a fundamental building block in programming. Let's move on to looping statements. Again, we see another table that lists languages and count controlled loop with a while statement. So here, this illustration is for looping structures like while and for loops. These enable repetitive tasks, making them essential for efficient problem solving. Subprogram statements. Subprograms encapsulate code under a name. When called, execution jumps to the subprogram, runs its code, and returns. This improves modularity and reusability in programs. Subprogram statements. Here the slide presents an example of subprogram usage, highlighting how methods or functions organize functionality and simplify main program logic. Here is an illustration of nested logic. I would request you to pause the video and read the algorithm line by line, understand if within a while how it operates, and let the idea sink in. Nested logic builds complex decision structures but can reduce readability if used excessively. Here we see one while loop nested inside another while loop. While powerful, deeply nested loops require careful design to avoid confusion. Again, you may pause the slide, read the algorithm line by line, and try to understand it in a deeper fashion. Moving on to the third slide for nested logic. It compares two different slides and asks you which one is easier to read. Readability depends on structure, indentation, and clarity, critical for maintainable code. Asynchronous processing describes actions not synchronized with the program's main flow. Mouse clicks are a common example. They can occur at any time and trigger independent event handling. Modern software relies heavily on asynchronous interaction. So basically, asynchronous means it's not synchronized with program's actions, and mouse clicking is not within the sequence of the program. A user can click the mouse at any time during the execution of a program. Moving on, functionality of object-oriented programming. Here we see that core OOP features such as encapsulation for hiding information, inheritance for reusing class behavior, polymorphism for handling duplicate names, and the idea that classes may have different meanings depending on context. I would suggest that you look up these terminologies to have a deeper understanding of these ideas. These are very important ideas if you plan on having a career as a developer. Moving on, the slide distinguishes between the problem solving of view of objects and classes versus their implementation view. Conceptually, a class represents a group of similar objects. In implementation, it becomes a pattern instantiated as objects. Next slide is about class definition. A class encapsulates both data and actions. This slide shows the structure of a class, emphasizing how fields and methods together define object behavior. Here, this slide continues the class definition example, showing how classes are structured in code. Understanding these components is essential for creating usable objects. Class person example. It illustrates real fields and methods. It connects design concepts directly to code implementation. This slide further elaborates the class structure, showing how methods operate on an object's internal data. Again, I recommend that you pause the slide and read the code block line by line to understand it deeply. Now, this slide explains how objects are created using the new operator. Instantiation creates specific instances after which methods like initialize and print can be called. This is the final step in bringing class definition to life. Inheritance and polymorphism. Inheritance enables reuse by allowing new classes to extend old ones. Polymorphism supports duplicate method names across classes while selecting the correct behavior based on the object. Together, these features make OOP systems flexible and powerful. Inheritance and polymorphism again. Here, the idea is that inheritance and polymorphism work together to create class hierarchies. These hierarchies form reusable libraries, reducing development time and increasing consistency across systems. Top-down versus OO designs. In top-down design, we determine data structures, write subprograms to manipulate them, and then build main program that uses those subprograms. The process is task-driven and focuses on functions above all else. In contrast, object-oriented design begins by determining which ADTs are needed. ADTs are implemented as classes encapsulating their data. The main program simply instructs objects to act, making the design more modular and intuitive. Ethical issues. Here we explore digital ethics, asking about differences between hoaxes and scams, common user complaints, major online crimes, and why policing them is difficult. It highlights the importance of cybersecurity awareness in modern computing. This slide asks you to identify one of the computer scientists. He is a known figure for structured programming and witty observations about software development. Students are invited to reflect on structured programming here, structured programming principles, and recall memorable quotes from this influential thinker. Here, there are some questions being asked to you on how computers are used in tennis tournaments, what percentage of downloaded software contain malware, what predated bytecode, the evolution of word paradigm, and how many meanings the word bow can have. These prompts encourage curiosity about technology's role across diverse domains. I hope you enjoyed today's presentation. Again, I'll request you all to do a little more research on the vocabulary presented in this class so that you have a better understanding of what we learned just now. And see you in the next class. Thank you. Bye.